I am Ruchika Chauhan presenting our paper, An Adversarial Approach for Cross-Domain and Cross-Task Knowledge Transfer. The problem we want to tackle is that supervision is not available for all tasks in a particular domain. In this respect, our aim is to perform inference for a task for which ground truth labels are absent. We consider two dense prediction tasks, depth estimation and semantic segmentation, denoted by T1 and T2 interchangeably. Supervision is available for both tasks T1 and T2 for a source domain A. However, supervision is only available for task T1 for domain B. Here we want to perform task T2 for B using any information that we can extract from T1 and domain A. The only reported work learning across tasks and domains demonstrates that information sharing between tasks across domains can be performed in the form of a domain-independent transfer function at the feature level. This methodology has been referred to as ATDT, which stands for Across Task Domain Transfer, in the subsequent sections. In addition to ATDT, we also compare the results of our method with domain adaptation frameworks like Cicada and FCNs in the wild. We argue that ATDT suffers from the problem of domain shift, especially when the domains are from real and synthetic sources. As a remedy, we develop a novel framework that minimizes domain shift using adversarial domain adaptation. We also improve the performance on target tasks by employing better transfer functions that capture more information. So we consider a transfer function with unit-like architecture with spatial attention that ensures maximum extraction of information between the two tasks. This is the overview of our architecture for ADA-ATDT. The training procedure involves 4 steps which will be presented in detail. The first step is to train the base model N1 on task T1 for both the source and target domains. The previous work ATDT consists only of an encoder-decoder model trained on the union of the source and the target datasets. We see that this method causes the output of the encoder to have a domain shift. So to tackle this, we add a binary domain classifier that predicts the domain of the input image. The encoder, the decoder, and the binary domain classifier are together trained in an adversarial setup, which aids in tackling the domain shift between the features extracted by N1 for both A and B. We perform a min-max optimization on the weighted sum of the adversarial loss and the task-specific loss. The second step is to train the base model on domain A for task T2. The third step is to train a transfer function G1 to 2 to transform encoded features for task T1 to features of task T2. This information transfer is performed at a feature level. The transfer function is trained on domain A under the supervision of abstract deep features of both the tasks using mean absolute error as a loss function, as shown in equation 3. The fourth step is to test this transfer function on the target domain B. So encoded features of task 1 of a domain B are transformed to features of task 2 using the transfer function, which is then passed through the decoder, which is trained on domain A in step 2. We perform experiments on 4 datasets, 2 real and 2 synthetic. 2 real datasets considered are Skityscapes and Kitty, and 2 synthetic datasets considered are Cynthia and Carla. In the first case, we consider T1 to be depth estimation and T2 to be semantic segmentation. From the table, it is evident that our method outperforms previous works in mean intersection over union and pixel-wise accuracy. And for obscure classes, our model is almost 10 times more accurate. When we consider T1 to be semantic segmentation and T2 to be depth estimation, we have obtained a superior performance with adversarial domain adaptation. As a better transfer function is used, the predictions of T2 are further improved significantly, with almost a 50% increase in performance when A and B are Cynthia and Carla. We also perform an ablation study on the domain classifier. To select the best domain classifier, we perform extensive experiments on different objectives, namely the binary cross entropy, mean square error, and the WGAN. We also conduct experiments to choose a good value of the hyperparameter alpha in the min-max optimization objective for the base model, which is trained on task T1. The figure contains Dsne plots for semantic segmentation for different loss functions and different values of alpha. From this figure, it can be inferred that BCE is optimal when N1 is trained for semantic segmentation By means of similar experiments, we conclude that mean square error is optimal when N1 is trained on depth estimation. This is the Dsne visualization of features before and after applying ADA adversarial domain adaptation. In figure A, the output of the encoder is without domain adaptation, and as you can see, it is disjoint for the two domains. In figure B, the output of the encoder with domain adaptation is almost intersecting. In conclusion, to counter the problem of domain shift between source and target domains, we employ an adversarial domain adaptation training setup using a binary domain classifier. We demonstrate that our proposed method significantly outperforms ATDT by using models with 81% fewer trainable parameters. We perform experiments on a transformation mapping similar to UNet to ensure maximum exploitation of features for task transfer. Thank you.